Hi everyone, how are you all? I hope everybody is doing fine. So till now we have learned about sequences, types of sequences, whether they are convergent, divergent, oscillatory. Then we have studied some properties of convergent sequences. Now moving ahead, we have something known as series, and there is a fine difference between a series and a sequence. So we will learn about what a series is, how it is defined in terms of a sequence, and how convergence of a series is related to convergence of some sequence that we will see. All right. So what is an infinite series? So we will be talking about infinite series. Okay. Now for a sequence an infinite series is defined as summation n going from 1 to infinity an. That means I am adding A1, A2, A3, and so on. And we'll see whether this sum occurs or not. Okay. Now, let's see what happens. Now, for example, if you take a sequence AN, which is given by N, then this is nothing but 1, 2, 3, 4, and so on. So summation n going from 1 to infinity an will be 1 plus 2 plus 3 plus this. Now this will be very large. That means we will not have a definite sum. This will tend to infinity because I will keep on adding natural numbers and so on. So in this scenario, this particular series is not convergent, that we say. And in fact, we say that this particular series is divergent towards infinity. Okay, plus infinity. So we can see that an infinite series is nothing but the sum of terms of a sequence in order. We cannot disturb the order. All right. Now we will see how to define convergence of an infinite series. Now, if you look at S1, S1 is nothing but the first term of the series. S2 is nothing but the sum of first two terms of the series. S3 is nothing but the sum of first three terms of the series. So Sn is nothing but the sum of first n terms of a series. Now let us consider the sequence Sn, which is nothing but S1, S2, S3, and so on. So we say that the infinite series summation n going from 1 to infinity an converges if and only if the sequence Sn, which is nothing but called the sequence of partial sums. So the infinite series an converges if and only if the sequence of partial sum converges. And if limit n tending to infinity Sn is equal to L, then limit, in fact, then this sum n going from 1 to infinity an will also be equal to L. So eventually the convergence of an infinite series depends on the convergence of sequence of partial sums. So you should know the concept of convergence of a sequence to understand convergence of an infinite series. Okay. So an infinite series converges if and only if its sequence of partial sums converges. Now again, let us look at the example where your an was n. So if you look at Sn will be 1 plus 2 till n, which is n into n plus 1 by 2. Now, if you look at limit n tending to infinity Sn, it will be limit n tending to infinity n plus 1 by 2, and this is infinity. So since Sn does not converge, the infinite series does not converge. And in fact, the sequence of partial sum is diverging towards plus infinity. So we say that our series is divergent towards plus infinity. So we have two kinds of series. So series can be categorized into convergent series and divergent series. We do not have oscillating series. We have oscillating sequences, but we do not have oscillating series. So what have we done? We have taken an infinite series in terms of sum of terms of a sequence in order. Order does not have to be disturbed. Then the sequence of partial sums is defined, we say that the series is convergent to L if and only if the sequence of partial sums is converging to L, where L is finite, and the series is divergent to plus infinity or minus infinity depending on the case if the sequence of partial sums diverges to plus infinity or minus infinity. This is the definition of convergence of a infinite series. Now we will do something very important which is known as divergence test or nth term test. Okay, so this is a necessary condition for convergence of a series. So what is the necessary condition for the convergence of a series? If summation n going from 1 to infinity an converges, then limit n tending to infinity an is equal to 0. So if at all my series is convergent, then the nth term of the sequence an should go to 0. How? So suppose series converges, then limit n tending to infinity Sn is equal to L. Also, limit n tending to infinity Sn minus 1 is equal to L. It does not matter if I remove one term. Okay, so both the sequences of partial sums will go to L. Now, what is Sn minus Sn minus 1? So Sn is a1, a2 till an minus 1 plus an, and Sn minus 1 is a1 plus a2 till an minus 1. So when we subtract, we only get the term an. So now, by the algebra of convergence of sequences, limit n tending to infinity Sn minus Sn minus 1 is equal to limit n tending to infinity Sn minus limit n tending to infinity Sn minus 1, which is L minus L, which is 0. And the left hand side is nothing but an. So we have proved that if an infinite series summation n going from 1 to infinity an converges, then an has to go to 0. So the sequence an is convergent to 0. That is, we have proved. So we can use this result to, understand or to disprove that certain series is convergent or not. So let us look at an example. So suppose you are given the series summation n going from 1 to infinity n square. So here your an is n square. So if you see limit n tending to infinity an, this is nothing but plus infinity. So since the sequence is not converging to 0, this infinite series will not have a sum. So this particular result sometimes is very handy in eliminating the options in a multiple choice question where you are supposed to discuss convergence of a series. So I hope you understood what we learned today. We learned what is a series. Series is sum of elements of a sequence in a particular order. Order is not supposed to be disturbed. Then we learned convergent and divergent series, two types of series. Then we learned that a series is convergent in terms of convergence of a sequence of partial sums. And we also learned divergence test. That means if the nth term of the series does not go to 0, the series cannot converge. This we can confirm. But converse may not be true. That is, if the nth term goes to 0, we don't know whether the sequence or whether the series is convergent or not. So we will see that in the next class. So see you in the next class. These two types of series. Then we learned that a series is convergent in terms of convergence of a sequence of partial sums. And we also learned divergence test. That means if the nth term of the series does not go to 0, the series cannot converge. This we can confirm. But converse may not be true. That is, if the nth term goes to 0, we don't know whether the sequence or whether the series is convergent or not. So we will see that in the next class. So see you in the next class.